Another thing to consider is the pH of ocean water. Is the seawater acidic or is it basic? So first of all, what is pH? Well, pH, if we look at the pH scale, is simply a measure of how many hydrogen, H, ions are within that substance that you're measuring. So the hydrogen ions have the chemical formula of H+. An acid is a compound that releases hydrogen ions when dissolved in water, and this makes the water acidic. A base is a compound that releases hydroxide OH negative ions when it's dissolved in water, and this makes the water basic. So to determine the pH of something, we measure how much of a hydrogen ion is it. If we dissolve a substance, for example, if you dissolve rocks, some rocks have a lot of sort of acidic based elements within them, we can actually make the water more acidic or more basic. So what is the acidity of seawater? Or more importantly, or more accurately, what is the pH of seawater? We find that the pH of seawater is variable. It sits somewhere between 7.8 to 8.3. There are no units with pH, it's just a unitless scale. So this makes seawater slightly basic. Well, seawater is basic, but when water, H2O, combines with carbon dioxide, CO2, and there's a lot of carbon dioxide in the atmosphere, and we're increasing levels of carbon dioxide every year, what we see is this chemical formula right here. H2O, water, plus CO2, carbon dioxide, gives you hydrogen, and HCO3. And we know that hydrogen is how we measure pH. This, how many hydrogen atoms are added to water increases the acidity of water. So this process of combining with carbon dioxide, we'll see that water, the ocean is actually a really great carbon sink, should be making the seawater acidic. Why isn't seawater getting drastically acidic over time? Well, ideally, and we'll see there's a big but here, we have buffering occurring. And this buffering occurs to minimize changes in the pH and preventing the ocean from getting too acidic or too basic. So what we have in the ocean is a carbonate buffering system. This helps keep the pH levels ideally between the 7.8 and 8.3, but as we'll see in the next slide, conditions are changing and we're starting to see that the ocean water is slightly becoming more acidic. So for most of the time in the past history, this buffering system has worked really well. We're starting to see it breaking down now in the present day. What's happening is they're starting to see ocean acidification. The ocean water is starting to become less basic and is becoming more acidic. What is this believed to be tied into? It's believed to be tied into warming global temperatures. What we see is as global temperatures increase, it increases the amount of carbon dioxide in the atmosphere. Now we know that seawater when it's colder can contain more carbon dioxide, but also what happens is if there's more carbon dioxide in the atmosphere, the ocean's actually going to take up more carbon dioxide as well. And we know that that interplay, that chemical reaction between water and carbon dioxide results in a hydrogen ion. So if we add more carbon dioxide to the ocean water, we're actually going to increase the amount of hydrogen in it and therefore start to increase or make the pH drive more to the acidic side. So we're going to start to have ocean acidification. Maybe not the point that where if you walk into the ocean, your flesh is going to melt off of you, but as we'll see, this is going to start to play a role in the life of organisms that have shells. Remember the carbonate compensation depth when we talked about sediments, and we know that below a certain depth in the ocean, the water is acidic enough, or the acidity of the water increases, that shells made of carbonate start to dissolve. We're starting to see the same thing, or a very similar thing, in waters closer and closer to the surface, where we have this huge amounts of carbon dioxide being taken up by the ocean because there's just so much in the atmosphere. We're seeing an increase in the production of hydrogen. This results in a slightly more acidic ocean water. And what happens is we actually start to see some of these shells of these invertebrates, these clams, in this case here we have a small little gastropod or snail, they're starting to break down. They're starting to become, as the ocean becomes acidified, these shells are starting to become more and more weak, and some organisms aren't even to produce really strong shells anymore. So they break down very easily, and this has disastrous effects for the life cycle of that particular organism. We're going to go now back and start to talk about the density of seawater. So we've already talked about the density of water, and we know that water in its solid form is less dense than water in its liquid form. We're going to concentrate now, though, on the density of water in its liquid form. And once again, density, what is density? It's mass over volume. It's the relationship between the mass of a substance and how much shape or space it takes up, its volume. Here we have a little chart, and it sort of gives you an example of what a low density object might be or substance might be, and what a high density substance might look like. So low density, we might only have, let's say for example water, we might only have water of low density that we only have a few particles dissolved in it, a few dissolved solids. More dense water, denser water, what we'll see is that we have many more dissolved solids present within it. What we'll find out with seawater is that the density of seawater is a function of temperature, salinity, and pressure. Here we have two beakers of water. The one on the left is a beaker of pure water. The one on the right is a beaker of seawater. So once again, the density of pure water, if it's at 4 degrees Celsius, would be a 1 gram per cubic centimeter. That same amount of water sitting, let's say, at 4 degrees Celsius is going to weigh about 2 to 3% more. It's going to be denser. And that's because the dissolved solids, the amount of dissolved solids within it, is going to affect how dense that water is. So we can see the density of seawater can range anywhere from, in this case, about 1.022 to 1.03 grams per cubic centimeter. So we have the dissolved solids in it. We know we have water of variable salinity. We still have constant proportions of the solids, but the salinity can vary. What's going to end up happening is that the amount of dissolved solids in what we can think of as a package or layer of water will determine where that water will sit in the ocean, within the water column of the ocean. What we see quite simply is to increase the density, we have an increase in salinity, a decrease in temperature to colder water, and an increase in pressure. To decrease the density, we have a decrease in salinity or lower salinity levels, increasing temperature, and decreasing pressure. If you want to put this down into one simple sentence, cold, salty water is more dense than warm, less salty water. So you have water that's cold with a lot of dissolved solids in it. Where we're going to see it sitting? We're going to see it sitting lower down in the water column, closer to the ocean floor. Warmer water, water that's less saline, it has lower amounts of salt dissolved in it, it's going to be closer to the surface of the ocean. So if you look at water within the world's oceans, and we're actually going to look at this diagram again when we talk about oceanic circulation, what we see is density determines the vertical position of a package of water in the ocean. We find warmer, less salty water at the surface. We get deeper in the ocean, we find colder and typically saltier water at depth. And as a result, we have about 3 main layers of ocean water. If we look at the density and we look at the salinity, what we can see is we can sort of have 3 different zones. We have something called the surface zone. The surface zone is also known as the mixed layer. It represents about 2% of ocean water. And what we see is that temperature and salinity are relatively constant with depth. So you go a little bit deeper into the surface water, the temperature and the salinity there is going to be the same as close to the surface. The surface zone is only going to extend to, at the max, a depth of 1,000 meters, depths of about 150 meters is more common. Underneath the surface zone is the pycnocline, and this is representative of about 18% of all water in the ocean. What we see here is as we increase depth, we have a very rapid increase in density. Water temperatures are decreasing very quickly as well, and we'll look at that in the next slide. Then finally we have the deep zone, and this is the bulk of ocean water, roughly about 80% of all ocean water. Here we see very little change in density with depth. Water is cold, it might get even colder down towards the bottom of the ocean floor. The other thing you might see if you look at this very closely is that as you move further and further north or south, so towards sort of the left of this graph right here, we'll see that the surface zone starts to disappear. Now remember, warmer waters mean less dense water. So not only is density a function of salinity, but it's also a function of how warm or cold that water is. As we move further north, air temperatures are lower, the water temperature subsequently will be lower as well. So that means that when we get to the far north, we see that the waters that are typified by the deep zone actually extend all the way up to the surface, and we don't have the presence of the pycnocline or the surface zone. What is the pycnocline? The pycnocline is a zone of rapid change in density with depth. So as we get deeper, the density increases. You can see it right here on this little sort of bar graph or this bar chart. We have the surface zone, density remains relatively same. And then we hit the top of the pycnocline and we see there's this rapid increase in density. We also find that the pycnocline very closely is tied into the thermocline. Cline just means that we're seeing a change in things. The thermocline here is a zone of rapid change in temperature with depth. In this case here, we see temperature decreasing. And this makes sense. We know that the saltier the water is, the colder the water is, it's going to be denser. So as we have this rapid change in temperature, we see a matching rapid increase in density. Once again, it's going to depend on where you are in the world, whether you see the pycnocline or the thermocline. If you look at the thermocline here, we see it actually on the little graph on the right-hand side. We see that the thermocline very pronounced in temperate waters, very pronounced in tropical water. It's sort of in that little red band that we see on the graph, but it almost disappears in polar waters. And once again, when we're at those higher latitudes, we see that air temperature much colder. There's not that great of a change in temperature between the surface waters as well as the bottom waters. This also means that we're going to see changes in salinity as well. What we see in terms of changes in salinity is we see that it very closely mimics the pycnocline. So we also not only have a thermocline looking at changes in temperature, a pycnocline looking at changes in density, but we can also have a halocline or a halocline. This is looking at a zone of rapid changes in salinity with depth. And we see that it very closely mimics or follows what the pycnocline is. Not only do we have dissolved solids within seawater, but we also have dissolved gases. And the presence of dissolved gases is really important, especially from the terms of life. Fish need oxygen to live. Where is this oxygen coming from? What we would see if we were to analyze seawater is we find that there's oxygen actually dissolved in the water. Not only do we have oxygen dissolved in seawater, but we also see nitrogen and carbon dioxide. So some of these common atmospheric gases, and these are easily dissolvable in seawater. As we said, previously, we even see the levels of carbon dioxide dissolved in seawater increasing as we have more and more carbon dioxide within the atmosphere. These gases are all important, especially in oxygen and nitrogen, for marine organisms to live. And we see that it's roughly about 48% nitrogen, 36% oxygen dissolved within the water, and then 15%. But as I said, this is changing, carbon dioxide dissolved within seawater. We see that as water gets colder, the amount of dissolved gases increases. So colder water can actually contain more dissolved gases. We see this here. A lot more oxygen in water that has a temperature of 5 degrees Celsius than there is in water that has a temperature of 25 degrees Celsius. Same thing as well for nitrogen. As we increase the depth, so as we move into progressively deeper and deeper water, we see that we get less and less oxygen being dissolved in the water. And that makes sense because in the upper surface of the water, we have a process known as photosynthesis occurring. Photosynthesis, one of the byproducts of it is the production of oxygen. We're in contact with the atmosphere, so we get an exchange of oxygen between the atmosphere and the water. As we get into deeper and deeper parts of the ocean, what happens is we no longer see an input of oxygen within the system. So the amount of oxygen decreases, but the amount of carbon dioxide actually increases. What role do these various gases play? Well, we find that in the upper layers of the ocean, they're saturated with nitrogen, once again about 48% nitrogen. And nitrogen is required by many organisms for protein building. If you have gills, you're going to need oxygen. And we get this both from photosynthetic activity within the upper layers of the ocean, within the photic zone, and we get it from atmospheric diffusion. It basically filters in, it's diffused in from contact between the surface of the water and the atmosphere. And then finally, carbon dioxide, very soluble in seawater. Once again, this is why we're seeing levels in seawater increasing. And it's important as a carbon reservoir. So it's a place where we can actually store carbon to decrease the levels of carbon dioxide in the atmosphere. But as we see, this can have very negative effects on certain types of life within the ocean. We'll finish off this lecture, or this module, by talking about light in seawater. And when a beam of light travels through seawater, a number of different things can happen. This beam of light can be scattered. It can be broken up into separate little particles in a sense. It can be absorbed. Remember, light is simply energy traveling through a medium. It can be reflected, almost like light hitting a mirror and bouncing back, or it can be refracted. And refraction means that it's bending as it passes through the ocean, water. We find that light only penetrates to a certain depth within the ocean. In the tropics, light typically can penetrate to a depth of about 600 meters. In the open ocean, to a depth of about only 100 meters. Depends where you are. The distance, or that zone in which light can penetrate, is known as the photic zone. The aphotic zone falls below the photic zone, and this is where no light penetrates. We find most of the life in the ocean is concentrated within the photic zone, but we do have life within the aphotic zone as well. The depth of the photic zone is going to be affected by different things. It's going to be affected by how clear the water is and how turbid the water is. In turbidity, one definition is the optical determination of water clarity. So if you have a lot of particles not dissolved, but a lot of particles present within the water is going to be very turbid. It's very difficult to see stuff and it's not very clear. Turbidity is based on the amount of light scattered by particles in the water column. The more particles that are present, the more light will be scattered. So once again, we get a lot of material within that water column. The water is going to be very turbid. And we can see this actually here in this diagram here. There's this little white and black disc that's been lowered into the water to help us determine how clear the water is. And you can see the water looks very, very murky. In this case here, would say it's turbid. The more turbid the ocean is, or the more turbid the water is, the less sunlight won't be able to penetrate as deep as it would be if we have very, very clear water. Remember that light is energy. And energy moves in wavelengths. So we can take light and we can break it down into many different wavelengths. And what we're concerned about here is what we see in this diagram as visible light. We see that there's a certain wavelength for purple, the color purple, or what we perceive as the color purple. There's a certain wavelength for light that's perceived as the color blue, yellow, orange, and so on. We break light down to all its visible wavelengths. What we see is that blue light, the wavelengths that create blue light, penetrate deeper than all other wavelengths. So once again, it's energy. What happens is that energy is absorbed as it starts to travel through the water. So we find that the red colors and the orange and yellows very quickly sort of disappear as that light travels through the water. Blue, though, remains. It travels the furthest, sometimes to a depth of up to even 300, sometimes pushing to 400 to 500 meters. So the interesting thing here is if you cut your hand in the ocean and you're below a depth of roughly about 10 meters, what's going to happen is your blood's going to kind of have this gray color to it. It's not going to appear as red blood. And that's because that wavelength for the color red has all been completely removed. It's been absorbed by the water in the ocean. Once again, the important thing here to remember is that with some colors, the energy is absorbed, it's converted to heat, the wavelengths are absorbed, so we're not always going to see certain wavelengths as we move down deeper and deeper into the water column. Thanks for listening. That's the end of this module. Once again, if you have any questions, you know how to contact me.